Hey, ladies and gentlemen, this is Miss Humbert here. Today we're going to be doing Unit 6, Learning Target 4. So we're going to be talking about exponential growth. So we've been working on graphing exponential functions up to this point, and now we're going to look at specific type of exponential functions, and more specifically, how they apply to word problems. So let's take a look at what exponential growth is. Exponential growth takes the formula y is equal to c times 1 plus r raised to the t power. So c represents our initial amount, or our starting value. Okay, it also represents our y-intercept. R is the rate of change. Typically, we see it as a percent, but we can't leave it as a percent. We have to convert it to a decimal. So your rate will always be a decimal. And then T represents time. So that represents how much time. We want to make sure our time units are consistent throughout the entire problem. All right, let's take a look. So to change a percent to a decimal, you move the decimal left 2 places. So let's take a look at what that looks like. So here, if we wanted to convert this first problem here to be a decimal, we move the decimal point over 1, 2 places. So we get 0.124. So the decimal we would use to represent 12.4% is 0.124. Now if you're looking at 6%, there's no decimal point, but the decimal point follows after the 6. So we need to move it over 2 places. So that's going to become 0.06. So if there is no decimal point, it comes right after that number. Now I see here that I have 0.7%. So you can't just say, oh, it's a decimal, I can plug it in just because it's a decimal. No, you still have to convert that percent to just a decimal and not a percent. So we still have to move it over 2 places. So when you move it over 2 places, you end up getting 0.007. So again, all of those percentages need to be converted into decimals, okay? Next, let's take a look at number 1. So remember that formula, y is equal to c times 1 plus r to the t. Now our t is kind of like our x. It can change and vary. Okay, so let's go ahead and write the equation. Well, our c is 8. So we have y is equal to 8 times, now we have 1 plus 0.45. That comes from here, 1 plus 0.45. Well, that's going to be 1.45. So that's what's going to go in our parenthesis is 1.45. And that's going to be raised to the x or the t power. So this right here is what you are graphing. And then you're graphing it just like you did earlier in the units. Nothing has changed except this time we've written the equation. So my middle is greater than 1, so I'm going to do 0, 1, 2, 3, and 4. So you're just going to plug in each of these values up here. So you're going to plug in each of those values for x. So when you plug in 0, this is how you would type it into your calculator. 8 times 1.45 being raised to the 0 power. You're going to type that in your calculator and you get 8. Then when you type in 1, you get 11.6. Then when you type in 2, you get 16.82. When you plug in 3, 24.39. When you plug in 4, 35.36. So now we're going to graph each of these points. So we're going over 0, up 8. That's this point right here. Right here. And then we're going over 1 and then up 11. That's this point here. 11.6, I'm sorry. So we're going to go just over halfway, which is about here. And then we're going over 3 up 16.82. So that's almost to 17 right there. And then our next one's going to be somewhere off our graph. So as we're graphing this, we want to make sure that we don't cross over that 4 where you can see on the graph because it crosses at 24, which isn't on our graph. So that's a rough sketch of the graph from there. Let's take a look at another problem. So for this one, our c is equal to 6. So we have y is equal to 6, and then we have 13.4%. Well, whenever I see that percent sign, I know I need to convert it into the decimal. So the decimal of 13.4% is 0.134. Now remember that our original growth equation, we have to add 1 to that. So we have 1 plus 0.134, and that gives us 1.134. So that's what's going to be in our parenthesis, is once we add those together. So 1.134, and again, that's going to be raised to the x power. So now for my chart, I'm going to use 0. Now with growth equations, I usually start at 0. So I have 0, 1, 2, 3, 4. When you plug in 0, you get 6. You plug in 1, you get 6.804. You plug in 2, you get 7.72. Again, all we're doing is we're taking out the x and we're putting each of these numbers in as the exponents. So when I plug in 3, I get 8.75. Now remember, I always suggest you calculate along with me so you make sure you're getting the right answer when you do so. So what you'll notice is that this is growing very, very slowly. That's why our numbers aren't increasing that much. So let's go ahead and let's plot some of these. Okay, so we're starting at 0 and going up 6. So over 0, up 6. That's right there. Then we're going over 1, up 6.8. So that's almost all the way to 7. And then we're going over 2, up 7.72. That's almost all the way to 9. And then we're going over 3, up 8.75. Almost all the way to 9. And then 9.92, almost all the way to 10. So as you can tell, it's sloping up very, very slowly. But as we get higher, it'll start increasing more exponentially. It shouldn't have that little waver in there. My thumb slipped. Okay, so that's our rough graph of that chart right there. Now let's take a look at how this is going to apply to exponential word problems. So in 1971, there are 294,105 females in high school sports. Since then, the number has increased. So whenever you see that word increased, that means that you need to use an exponential growth equation. So it's growing at an average of 8.5% per year. Well, we want to convert that to a decimal. So we're going to move it left 2 places, and we get 0.085. Now that's our rate. So it's asking us to write an equation. Okay, so we're going to do y is equal to, well, our starting number of females is 294,105. Now, since it's a growth equation, we need to do 1 plus our rate. And that's going to be raised to the t, because we don't know how much time is passing because we're writing an equation. This isn't done. You actually need to add those two together. So your y is equal to 294,105, and then you're going to take 1 plus 0.085, which is 1.85, and raise that to the t power. So this right here represents that equation. So now we need to plug in our t. So we need to figure out how many females there were in 2005. So in order to figure out our T, we need to take what year we're shooting for, which is 2005, and subtract the year we're starting in, which is 1971. That was our starting year. So when you subtract those, you end up getting 34. So 34 years have passed. That's going to be our T. So we're going to end up plugging that in for our T value there. So we get 294,105 times 1.085 raised to the 34th power. So you can type this exactly into your calculator. So why don't you try that? Make sure you get the same answer as I do. When you do that, you should get 1004. So this is what you get. Then you get 0.36. Well, I don't want to talk about 1/3 of a female. I don't even really know what that means. So I'm going to look at this decimal. Since it's under 5, I'm going to keep this number the same. That's the rounding. So I get 4,711,004 females that are participating in sports. So whenever you're talking about living things, you always need to round to the nearest living thing. Let's take a look at number 4. In 2010, the city of Farmington had a population of 21,087. Okay, so that's going to be our starting point. The growth rate of 1.9%. Growth rate, okay, I need to use exponential growth, but I also need to convert that percent. So I need to move the decimal point over 2 places. So I get 0.019 as my rate once I convert that percent. So let's write that growth equation. So we're going to take our starting value of 21,887 and we're going to do 1 plus our rate. and that's going to be raised to the t power because we don't know what t is right now. Please make sure you actually add out that middle part when you're writing the equation. Don't be lazy, just add the two together. It doesn't take that much more work. So this is the equation that represents the growth in Farmington. So now we want to see what would the growth rate be first in 2013. So we're going to do 2013 minus 2010 means that 3 years have passed. So we're going to plug in 3 for t for the first one. So we're going to have 21,087 times 1.019 to the third power. And when you do that, you get 22,311.94. Again, I don't want to talk about what 0.94 of a person is. Well, this number is greater than 5, so I'm going to round this number up. So I get 22,312 people. So in 2013, we'd expect that there's 22,312 people. Now we need to do 2017. Well, then 7 years have passed, so that's what I'm going to plug in for t instead. So 21,870 times 1.019, and raising it now to the 7th power because 7 years have passed since our original date. And that for that one, we get 24,056.5. Okay, well 5 is 5 or greater, which means I need to take and I need to round this number up. So I get 24,057 people in Farmington in 2013. So that's our final answer for number 4. Let's take a look at number 5. The DNR has been tracking deer population since 1970. At the time, the deer population is 500. Okay, that's our starting value and has been increasing. Okay, I need to use growth at a rate of 5% per year. Well, I need to put 5% into a decimal. Well, that decimal point right now is coming after the 5, so I'm going to move it left 2 spots. So my rate is 0.05. The first question asked me to write an equation representing the deer population since 1970. So let's write it out. So we're going to have our starting value, which is 500, times 1 plus our rate, which is 0.05, and we're just going to raise it to the t power because we don't know what the time is yet. Well, I do actually have to add those together in order to have my completed equation. So that just becomes 1.05 raised to the t power. So that right there is the equation representing the deer population. Now it wants us to figure out what the population is going to be in 2017. Well, our starting year was 1970, so we're going to take our future year, which is 2017, and subtract our starting year. And when we do that, we end up getting 47. So 47 years have passed between our starting date and our predicting date. So that's the number that I am going to plug in for t. So then I have y is equal to 500 times 1.05, and now I'm raising that to the 47th power. So again, you should be plugging this in your calculator with me to make sure you get the right answer. So when I plugged it in, I got 4,952.98. deer. Well, 0.98 of a deer doesn't make sense. Well, that 9 is 5 or greater. So I need to take this number and round it up to 3. So I get 4,953, and I'm going to label that deer. So that's how many deer we're expected to have in 2017. So that concludes your note video today. Show me your completed note sheet when you're done. Thanks for listening.